Hey there, this is just a quick exploratory video of MetriCal, Tangram Vision's production line calibration platform. And I'm going to just jump right in with some of the prerequisites. So first off, MetriCal is a fiducial-based calibration system, which means it relies on targets to get ground truth fast. That's kind of where we get our speed. So the first thing you'll need before you even start is a target or targets. MetriCal can use multiple targets at the same time as long as either the targets are still and the rig is moving, so kind of moving a camera this way and that, or the rig is still and the targets are moving. So you can imagine me holding one of these, and this is our camera LiDAR calibration target, and kind of just moving it around the scene, getting good coverage. Right, and we'll get into what good coverage means later. But here you can see kind of the outline of a target. So we take Truco boards, checkerboards, April grids, caliber style grids, and we're engineering a couple more. But those should be a good cover for you no matter what you're doing. You notice that this Truco board is actually in a circle, and that is because this is a camera LiDAR registration board. So MetriCal uses this specific shape to register LiDARs to a camera system. This is a retroreflective piece of tape on the edge. When you print out a camera LiDAR board, you actually don't need it to be in a perfect circle. Like, this doesn't need to be cut this way. Since the LiDAR, we're only going to be looking for the LiDAR signal reflecting off of this tape. So when you construct your own board, you can use a square Truco board and then just put a ring of retroreflective tape around it. So that's that. Once you have those configured, depending on what you're doing, you're going to create what we call an object space. And so that's this file on the left right here. So if we zoom in, we can see that this object space is describing 3 boards. The first, or all 3 are going to be what we call marker boards. So this is what we call a Truco board. And their checker lengths, width, height, dictionary are all described here. This is all MetriCal needs to know in order to get a calibration. It doesn't need to know anything about your system. It doesn't need to know CAD. You don't have to give it specific extrinsics, although we can use those later on, as I'll show you in the results. But MetriCal works from zero knowledge of your system to give you a good calibration with 2 lines of code, right? That's kind of the promise. But it does need to know what to look for. So here, this first data set is going to take 3, going to be looking for 3 marker boards. We're going to see there be arranged in a square. Again, MetriCal doesn't need to know how these boards are arranged. It will figure that out itself. It just needs to know what to look for. So once we have that described, we can actually come over here and learn what we're actually going to be running. So like I said, MetriCal works in about 2 lines of code, specifically 2 lines of script. Those 2 lines are MetriCal init and MetriCal calibrate. Both of these are going to produce what we call a Plex. Plex, in the parlance of MetriCal, is a snapshot of your calibration at a specific point in time. So you can think of, when you're multiplexing signals into one sensor fused position, the Plex gives you that multiplexing ability, right? Clever. So all we're doing here in MetriCal init, this first command, is we're saying I'm working with topics named infra in my MCAP, which we can attempt MCAPs or ROS bags. Any topic with the keyword infra in it, infra star, I'm going to assign a camera model of no distortion. Now, there are 8 different camera models we can work with in MetriCal. Among them, double sphere, EUCM, OpenCV, RadTan, many, many more in the documentation. But for now, we know these cameras have pretty minimal distortion, so we're just going to say calibrate with no distortion. And my IMU, I'm going to give the model of scale, shear, and rotation. There are also 5 models For IMU intrinsics, you can have no intrinsics, scale, scale and shear, scale rotation, scale rotation, and G sensitivity. You can be as sensitive as you want as long as you're perturbing it correctly, which we'll get into later on as well. If you had LiDAR, you know, say your LiDAR was called Velodyne. If you had some Velodyne data, you could say all my topics that have velo, which are point cloud 3s, I'm going to assign the model no offset for LiDAR. There's only one LiDAR model, which we only do extrinsics. So this no offset is assigning that. So when it takes the models that we want to assign to our certain topics, and it takes the data that it's going to be reading in, and it's going to produce what we call this smithed Plex. So this is just going to output a file that's named initplex.json, which we're going to be using in the calibrate mode. When we look in the initplex, which you never really need to do, but if you were to open this, you would see all of our parameters. They're raw kind of guesses at what our calibration should be. So for instance, this camera has an RDF basis. It has very standard no distortion model. We kind of just guessed at this. We'll be solving for focal length CX and CY during the calibration. If you had a more complex model, you would see those parameters here as well. Again, init would just guess and kind of seed it with a result. We have covariances, input covariances for each and every one of these. So that's important because MetriCal will output covariances. So if you use a covariance, if you modify the output covariance or the input covariance to be very restrictive, you'll see that reflected in the output covariance of a MetriCal run. Generally, we say don't touch these covariances going in unless you know what you're doing, because MetriCal will solve them based on the data given, right? As we go down, you know, we read in all of our cameras, and now we can see our spatial constraints. Spatial constraints are identifying the translation and rotation between each component. If they're co-visible components, so they say you see the same target at the same time, they will automatically be assigned a spatial constraint, and that will be solved for during a MetriCal run. Then there are temporal constraints, which describe the synchronization between sensors. So if you have a certain hertz, certain frequency of observations between cameras, for instance, we'll use that to guess at the resolution and synchronization of your temporal constraint, which will help during the calibration run. So those are all the raw things we'll be solving for in a MetriCal run. Intrinsics, extrinsics, and temporal sync will be used as an input to the data. Once we run init, we use that smithed-plex output to then input into calibrate. This may seem funky, but what this allows you to do is actually take a output calibration and then seed it into another calibration. So if you really knew, if you had certain tolerances, for instance, of what you wanted your calibration to be, you could seed that in calibrate mode, and then it would act just like the naive smithed plex, but now just with tighter covariances, more certain metrics, etc., etc. You can, MetriCal calibrate will apply a motion filter to all the data in order to grab what is essentially the most important data, the most useful data for a calibration. For cameras, the motion filter is an average motion of 1 pixel per identified feature in the frame. So if you're sitting absolutely still, you'll only get a certain grid of features, and each of those features will be taken into the calibration because, you know, it's being filtered for motion. You can actually adjust this value. So usually the default is 1.0. We've adjusted it to 5.0 to allow more data in. This is saying on average, if my features shift 5 pixels frame to frame, I still want to allow that motion in. This is helpful in camera IMU calibrations just because you don't want to throw away so much data that your IMU doesn't register between two cameras, but usually you could just leave this default. So with that, we're going to pass in our data, our Smithplex, and our object, and we're going to output to this directory output, where can we see results camera imu.json. This is going to be a huge results file, lots of metrics, more metrics than you need. But at the end of that, you're going to be able to parse the metrics, the uncertainties, the variation between your inputs and what was output. Anything that you could use as a go, no go on your production line pops out here. MetriCal display is our last and most fun command. It's not actually going to do anything with the results, but render them. So we're actually going to be able to see a sensor fused calibration at the end. So let's go ahead and run this. We'll move my screen up here. Here we go. Let me move me in the corner. So now that we've done this, I can close this, and we'll just run init for now. So if I run this script with just MetriCal init highlighted, let's see if I can shift this over. Yeah, so here we're just running MetriCal init, as you can see on the top here. If I do this with the -y command to overwrite our other result, input data path is not provided. Oh yeah, of course. Live coding. You can see it's pulled out the topics that matched our substrings and assigned them a UUID and a camera model. So we had two topics that matched the infra substring in our MCAP. This was RS Infra 1 image raw, RS Infra 2 image rect raw. And then we had one that matched the substring IMU, that was RS IMU, and we've assigned that model as well. All other topics have been ignored. So now we've written a Plex. With this information, we can now go over to our calibrate mode and run that as well. So when we run calibrate mode, a couple of interesting things happen. It will run through and detect everything it can in each of these streams. So for images, that would be the board detections for every board listed in the file. For LiDAR, that's all LiDAR detections. For IMU, this is just the raw stream of IMUs. We don't do any pre-processing there. It will then cache those detections for future use. So if you then have to run this data set again, as I just have, you'll be able to pass the detection stage altogether and just go straight to optimization. Really handy if you want to be tuning and trying out different models or tuning your different motion filters, finding something that works for you. You don't have to go through the detection step again, which is usually the longest process. So here you can see we found some cache detections. We're going to be using those. And MetriCal will start telling us how useful our data is for calibration. Here you can see we've used all of the red observations in the IMU because we don't do any motion filtering there. For the images, we do motion filtering based on, again, the camera motion threshold here. And you see that we've gone from 2,137 observations for this camera all the way down to 300. So only 300 actually fit our criteria of very little movement. Same for the second camera, we have 306. So I would encourage you as a user to use the motion filter as much as possible. MetriCal's motion filter allows it to get rid of a lot of unnecessary data in especially camera captures so that you understand just the bare minimum, I guess, needed to get the best calibration, which will really save on computation time. So then we can see percent coverage by feature count, or coverage by feature count, rather, not percent coverage. So this is basically a binned feature coverage. of each image. You can imagine this is the top left corner of this image. This is the bottom right corner of the image. And here are all the features we captured in between. You can see this is a very feature-rich map. I would say this is a great capture. You want to avoid reds, especially in the corners, because when you're fitting a calibration to, or fitting a camera model to a calibration data set, you're going to want to fit the entire space of the image, not overfit within the middle. So even though we have a bunch of features in the middle, I would still say this is a very well taken data set and wouldn't feel bad about processing this at all. Same for the second camera. So we can safely say from these pre-processing metrics that this data set is probably good to go. This is a detection timeline. So this is just a timeline of your events. This is mostly here for a gut check. If you've written your timestamps incorrectly, you'll know from this timeline. Usually you'll see 2 or 3 components that have beautiful timelines, kind of like this, and then a fourth that just has like a big clump of dots on one side or the other, where you just, we're off by a year or 2. We've seen decades. So really, this is just a gut check to make sure that you've written your timestamps correctly. At the end of that is the actual calibration. You can see it was done fairly quickly. I think this 58, this was done in a minute and a half. So we went from 0 knowledge to a full calibration in a minute and a half, given a pretty dense data set. Even complex data sets with dozens of cameras, literally dozens of cameras, will take about 5 or 6 minutes to process. So MetriCal is designed for speed. It's designed for, this kind of pipelining in a production line. And then at the end, we have calibration metrics. So like I said, a lot of these metrics are in the results JSON, although you can also find them pre-printed here in the console. So if you're looking for something specific, it usually just shows up here. First, we're going to revisit that binned graph that we had above, but now we actually see the reprojection error instead of the number of features. And you can see this reprojection error is very good. Even in the corners, we're getting less than half a pixel. So, really good calibration. Clearly, there was very little distortion in this. It worked really well. But even if you had a different model, I would expect this to be the case with that kind of data that we collected. Here, if you have a stereo pair, MetriCal will automatically detect cameras that are in a stereo configuration. So both looking forward and having a certain baseline between them. And then you can have binned rectified error output for those matching features. So here the dominant eye was in for 1, secondary eye was in for 2. And if you rectify those 2 cameras, you have an average RMSE of 0.2 pixels. Very good for stereo rectification and depth synthesis, for instance. So if you're recalibrating a set of real senses, this would be where you look to make sure that that calibration that you derived is actually best for your system. In this case, it is a real sense, RS in for 2, RS in for 1. So when we flash this real sense calibration on, I would expect it to give great results. Then we have some IMU metrics and extrinsics metrics. Between every camera, we'll have a relative extrinsic RMSE, telling us the average error from our detected features of the extrinsics. These are very tight. I mean, this is less than a millimeter of error in each of these axes, as well as less than, like 0.02 of an error in rotation. So very confident in this extrinsic result. IMU pre-integration errors give us something very similar, but IMU is registered to object space. So every object space that we have in the scene will have an inertial frame, and therefore the IMU will have an extrinsic reference to that as well. And again, these are very good metrics. I would be very confident in these results. Here's our optimized camera metrics. Here's just the optimized pinhole distortion, or the pinhole parameters. If you had a distortion model, it would show up here. And here are all the optimized IMU metrics that we derived as well. Here's the final extrinsics result. We know for a fact that RealSense have a 5 centimeter baseline, this is a good check for that. If you had put in your own previously generated calibration as an input here, this is where you would see the difference in the input between that calibration and this one. Obviously, we had an identity put in here, so it's exactly 51 millimeters off as expected. But if you had certain tight tolerances that you were expecting mechanically, you could gut check them very quickly here, in addition to pulling out the value in the results JSON. So yeah, that's a lot, but that's kind of what MetriCal is designed to do, is give you a lot of details about your the quality of your calibration. So now let's do the fun part and run MetriCal display. This is when we actually are, this is a previous run of this same data set, but you can see how we've visualized exactly the data set here. Here, let's back up. So if we play this, you can see these 3 boards that we were talking about at the outset. They were in a square design. We didn't need to know it was a square. MetriCal figured that out, as you can tell by the features here. In fact, you can see one's even leaning a little bit, which is cool. Here's the raw IMU. Here's the extrinsics of the Plex. Looks exactly how we would expect. And you can play around with this both in init mode or in calibrate mode and display mode to see how these features came out and examine the results of your calibration. So that's it. I mean, all we did was run 2 lines of code, but we have a wealth of information at our fingertips. And MetriCal is really as powerful as you want it to be in that you can script everything here and have the process be completely automated, right? Or you can be running in an R&D and just have all this information at your fingertips to kind of hone your process and make it better. So yeah, that's it. Thanks for joining me on this MetriCal adventure, and I hope it's useful to you.